Hello everybody, welcome to our next MetFlix video. Metsoc.mcgill student chapter is here at CEP Sintra with Nicolas Geoffroy. Hi. I'm Constantinos. Here's Yiwei, Andre, and Christina. So, Nicolas, please tell us a few words about your job here as a forensic engineer. And what exactly do you do? It's a really interesting subject, and it's really interesting for materials engineer students to learn more about your responsibilities here as an engineer.
Basically, we're CSI, but for basically anything that failed. So I'm a materials engineer, so I specialize in materials that fail. So it could be anything from plumbing parts to industrial machine, industrial equipment. Sometimes it's civil, so paint that peel, for example, corrosion of underground piping networks, things like that. So anything that failed and involved materials. I don't work a lot with polymers, but I have colleagues who do that also, work exclusively with polymers and organic material. So we basically, that's it. So we try to determine why materials fail, and we mainly work for insurance companies. Okay, so 95% of our clients are insurance companies who want to know why something failed in order to see if they can basically subrogate, which means sue someone to get the money back that they paid to settle the claim. So we work a lot with lawyers also. So it's a lot like CSI basically, but instead of running after criminals, we run after poor materials or poor designs or things like that. So we deal a lot with lawyers. I testified 3 times in court also.
I guess like in the follow-up of the questions, so your job, how did you wind up here at CEP?
When I finished my PhD at McGill, I started to work for a year and a half at Technical Technique. So I was kind of doing this, but in an academic setting. So we were doing R&D projects for companies. Okay. So it could either be a very small thing where they would want to use a machine, the XPS or the SCM or something like that. Or they wanted to do larger projects. So I was handling that for them. So I did that for about 18 months. I liked it, but I didn't. It was kind of a slow pace and it was slow going. So and then I moved to a general consulting firm, so a general engineering firm basically, and we were doing mainly oil and gas. Okay. So I was doing a bit of metallurgy there, but also general process engineering. So calculating flow and valves and things like that. And then there was kind of a downturn in the market for the oil and gas, and so for different reasons, I moved over here, okay. And I really liked it overall. So yeah, that has been very interesting experience. So I gained a lot of knowledge from the 2 previous jobs, and things that I can apply now to this job. Yeah.
And you've been here for?
Close to 4 years. It'll be 4 years in May now. Okay. Yeah. So I've worked on probably a few hundred projects. Wow. So they range from very small plumbing failures, which are the most common things we do in materials. So if something breaks in your faucet or a hose or something like that breaks in a house, it floods the house, so it can really add up pretty quickly. Okay. And then and it goes to the biggest loss I've done was about 350 million, something like that, like in an industrial setting. So. Yeah.
Due to plumbing also?
No, it was a corrosion thing, but I was part of a group of experts basically. Okay. But but I've done 40, 50 millions, a few of those. So it really ranges from 20, 30,000, the smaller losses, up to several $1 million for the bigger ones.
Wow. Yes. Impressive.
So your customers are more individuals or companies that had a failure?
Almost always companies. Occasionally we'll do directly private companies for different reasons. Usually it's fairly large losses, but I would say 90 or 95% of our clients are insurance companies. We're very well, they know how the process works, they know when they hire us, they know we're going to tell the truth basically. And sometimes it's in their favor, sometimes this is good for them, and sometimes it's not. And we occasionally tell the insurance companies, listen, you're insured, basically. Let's say if they insure a plumber or an electrician or something like that, and it's as long as it's their fault, this is why the building burned down, or this is why it was flooded. And I think it would be in your best interest to just settle the claim and stop investing resources in basically a lost cause. So basically, we're not lawyers. We tell it as we think it is. If we represent the manufacturer of the gizmo that broke and we think it's a manufacturing issue, well, we think it's a manufacturing issue. But most of the bigger failures, they have there's not a single cause, like there's different causes involved. So the most common example I give is an oil tank for a house that leaks and creates like a big environmental mess, eating oil. And often like the tank was poorly designed to start with, was not well installed, was not well maintained. So then there's a leak, the tank empties in the basement basically, and then it's very expensive to clean up. And in the end, you're like, well, there's not a single cause. If the maintenance had been done properly, they would have figured out that there was something wrong. If it had been installed properly, it would have lasted longer. If it had been properly designed to start with, it would have lasted longer. So often there's not a single cause, and that's also the challenge of explaining that, let's say, to a judge, saying, well, there's not often. They want to know who's to blame. Well, there's more than one, so that's been.
It's never black or white.
It's never black or white, and later today I have a call with underwriters. So large industrial projects, they're insured by often multiple insurance company. If the loss you want to cover is if the project is worth $1 billion, it's not a single company that's going to insure that. It's going to be multiple. So and then you have to explain to them, well, what happened, and then, well, I think you have an option of subrogating, basically suing this party, and this one is, and that's it. So it's never black or white. It's almost never black or white. So it's shades of gray.
I think that this goes into the question about like how is your day-to-day basis work like this? Do you spend more time meeting with clients or more time in the lab?
It varies. That's the interesting thing is that it varies. So a lot of what we do is, well, it also varies from group to group. Okay, so the people here, there's quite a few people who do fire investigation. They spend a lot of time on the road and they spend a lot of time on site. Like if a building burned down, they clear out the debris and they want to figure out why there was a fire. So I think overall they spend more time on the road and on site than doing other things. For materials or mechanical, we spend quite a bit of more time in the office, either in the lab or writing reports. And there's also quite a bit of project management. If it's a small plumbing failure, we'll maybe go get the part on site. And so there'll be a bit of traveling, of looking at the site, trying to gather as much info as we can. Sometimes the part is sent through mail or a messenger service. And then we're going to basically quickly analyze it in the lab, see what we think, if it's a good or a bad case. Let me give you an example. If it's your house and you have a dog and the dog chewed on the plumbing connector, which sometimes happens, but we look at the part and we're like, well, an animal chewed on it. There's no subrogation because it's the fault, quote unquote, of the owner. It's their animal who did that. If we get a part and it's the plastic section is snapped in half, then we say, oh, maybe we could subrogate against the person who installed it or the manufacturer of the part, something like that. So that's the first thing often we do. We look at the thing and we're like, is there potential in this thing, or it's, there's nothing we could do with that. Because the insurer, if we tell them, well, it's pointless, often they won't want to go forward. But for larger projects, also quite a bit of project management, looking at all the documents, classifying all the documents, reviewing them, planning the travel, planning the calls, the conferences, things like that. And so there's a site part, there's a lab part, there's project management, there's also report writing. So in this job, you have to write quite a lot. So we have reports ranging from a quick email and maybe a few paragraphs to full-on reports that can be 30, 40, 50, occasionally 200 pages with all the appendices and things like that. So writing is a significant part of what we do.
That you have a simple case, but also more complicated cases.
Yeah.
I was wondering, do you hire students as co-op students, for example, to help you in these? And generally, do you have a training program for the students?
Yes. So it's going to be our third year in a row that we have co-op or interns, basically interns. So what they do basically is two things. They help with project documentation. There's a lot of basic documentation. Let's say that mug failed for some reason. Well, something I've seen happen, not here, but somebody was pouring coffee and the bottom shattered and they spilled coffee on them. So that was in Europe, so nothing happened. But if it had been in the US, maybe there would have been a lawsuit. That's it. But so there's a lot of basic documentation. So we go in the lab, we take pictures from every angle, and that's also part of the process. Is that everything we do to start with is only visual. We don't destroy anything. We don't cut anything. We don't because we want to give the opportunities to third parties to have a look at the part in original. So that's also something very important. If there's a part you don't know who the manufacturer is, you don't know where basically it came from, sometimes it shuts a lot of door for subrogation because who are you going to sue? So there's a lot of basic documentation, and for interns we also have them work on more general research projects. So last year we had a student working on freezing failures. So pipe that freeze and things like that. It seems straightforward. The pipe freezes and it breaks and that's the end of it. But where is it going to break? How quickly is it going to break? If you get something that is flexible, is it going to absorb enough deformation to be able to resist the freezing, the plug that is created in the pipe? If you have a copper pipe, a plastic pipe, and a valve, is it going to break? Where is it going to break? In the solder joint, in the valve, and things like that. And so occasionally we had people say, oh, it couldn't be freezing because it leaked there and it would have leaked somewhere else. But we had the impression that it was based out of nothing. It was just the thing. So we did a lot of testing and we were able to figure out, this is likely, this is unlikely. And we get the students to work on that because this is not directly billable to a client.
So when you say you investigate more, do you also collaborate with universities, or is it just internal in CEP?
It depends on the side of the project. What we often do with McGill and also University of Montreal is we use equipment. Okay, so we're going to use their services to perform basically to use specialized equipment that we don't have in house. For example, we have optical microscope and we have an FTIR, so Fourier transform infrared spectrometer. Other than that, we're going to go to universities. Once in a while, we're going to collaborate with a professor, but that's really once in a while, basically. What we do most commonly is use the equipment ourselves, or we send. So probably today, I'm going to send samples to McGill to have to do X-ray diffraction.
It's interesting that you have different cases that require different methods of characterization.
Mm-hmm.
So in that sense, what kind of characterization techniques you use more often, and how did the university prepare you?
Well, what we use most often for sure is optical microscopy. So we have two good. So first thing is macro pictures. So we have professional cameras, so we take good pictures. Often we'll get pictures from third parties, and they're blurry and they're dark, and you don't see anything. So this is not what we want. No, but you would think it would be, especially now with digital cameras, but this is often not the case. Or somebody put their finger in front of the lens, and we get that also pretty often. So we take very good pictures that really document the condition of the part when we get it. So this is macro mode, as macro as it gets. And then we have optical microscope that can go, for the metallographic one, I think up to 1000x. So we'll take picture with that we can just walk in, put the part in. And the other advantage is that we don't need to cut the part. If it's large, we can slide it underneath, take pictures, and this is good. We have an FTIR. Now we have two, so we can, for polymers and organic materials, pretty much useless for inorganic material, but we use that to determine what kind of polymer it is and why if there was degradation. So those we have in house, and they're probably the things we use them most often. When we want to work on metals higher resolution or get chemical analysis, as a semi-quantitative chemical analysis, then we go to the SEM. The limitation of the SEM is that, well, first we have to travel to get there. And also, occasionally, we need to cut the part to fit it in. And this can be an issue when there's other parties involved and things like that. So if we need to cut the part or there's third party involved, we'll need to wait a little bit to get the other parties involved. Occasionally, we'll go, a few people look at the SEM and be like, oh, do you want to look at this, at that? And we'll do the examination together. Or occasionally we'll say, no, that's fine, you can go on your own, and then we'll take the samples and we'll do our own investigation.
I think everybody understands that all this information you have are really confidential for your clients. But you mentioned that sometimes you can go deeper. You can collaborate with university professors. Is it possible to publish something out of it, or in a conference or in a journal?
Yeah, what we often do, publishing a paper in a journal is not necessarily that common because you need to invest a lot of time and effort into it, and it's difficult when you're busy with a lot of projects. However, what we often publish is kind of white papers, if you want. Mm-hmm. So if you look on our website, we'll publish different things about different common types of failure. It wouldn't necessarily be only in materials or mechanical, but it could be in civil. Why do roofs collapse under snow load, for example, or why do basement gets flooded and things like that. So we often publish these kinds of white papers, or we present in conferences, and we basically describe generally the type of failure. So there's kind of a fine line between what we can share and what we cannot. Often we can generally describe typical types of failure, or we can even describe a specific failure, but we cannot identify who the parties were. And the other thing is that document reports that are filed in court, they become public. Okay, and once a case is settled, it's either there was a trial or more commonly the party they get to an agreement. Then this is basically public. So if we wanted, we could share it out, or we could go to the justice hall and request these documents.
What kind of skill set would you be looking for a student that would be coming here? What would you be looking for a certain type of degree or experience or a certain level of, I guess, maturity in the studies? Would you be more looking at people who have done a PhD, for example, things like that, or?
Well, first of all, I'm the only PhD in the company,
okay.
So I know
it's interesting to know because depending on what you look for, it would be different.
So that's it. So it would either be people with industrial experience or people with some kind of research experience. Do you need a PhD? Absolutely not. Mm-hmm. However, is that a good reason or not? But it impresses in court at least, or it impresses third parties. You have a PhD. That's impressive. Okay. You must have a lot of knowledge, even though it might not be at all work then. But so it's nice to have on your CV. You have a PhD. It's a nice letter to put at the end of your signature and things like that. But I guess it takes more than that. And often people will get the stereotype that, you're a PhD, you must be a rat lab, wearing sandals with socks and dressing in brown pants and things like that, which I guess is true occasionally. But so that's it. So you need to be able to communicate also, write good reports that people can understand, and be able to basically simplify. So I think it was Richard Feynman who said, if you're not able to explain something to a child, you don't really understand it. Mm-hmm. And this is kind of what we have to do. You got to explain to people, who claims expert or lawyers or a judge or whoever, something that is occasionally fairly complex, and say and basically not dumb it down, but basically go to the essence of the thing and say, well, listen, this is what happened. You don't kind of need to know every single tiny detail, but this is what happened.
But still, your PhD, everything you mentioned is skills that a PhD student develops through their studies, right?
You would hope so, at least. You would hope so. But it's, how could I say that? So we've had some people, not necessarily people with PhDs, but we've had some people who don't like to argue with others. This is what we do. We argue with others. We had a case recently, like the manufacturer was saying, well, they went above the maximum of the machine by like 3%. And we said, well, it's not very clear how they calculated that. And even if it was, there's no safety margin, you go above 3% and the thing breaks apart like it explodes. That doesn't make sense. Mm. And basically, there was a discussion, but did we really go above that 3% and things like that? But in the end, we said, even if it did, it shouldn't, maybe long-term damaging the machine, but it shouldn't create that type of damage. And that's often something we'll say. We've had employees before who had more of a research background and they wanted to go too deep in everything. And it's where do you stop, and that's often there's often a fine line over there. If you stop too early, you miss stuff and things like that. But you cannot turn every project into a PhD project. It's going to take too long. It's going to be too expensive.
It seems like you have been working on different cases with interdisciplinary professionals.
Yeah.
And I'm wondering what are some of the new skills you learned that you didn't learn back in university years?
Well, basically in university, I think especially McGill is fairly theoretical. You basically don't learn about any code, about any regulation, about any laws and things like that. And this is something that is very present in our field. Okay, so and also how how it works in practice in the industry and how things are done, there's like the ideal way of doing things, how things are done in practice. This is all things that I didn't know when I graduated from McGill anything about the SME code about the pressure vessels or the plumbing code or the fire protection code NFPA and things like that. And these are things we work with every day.
So generally, what would be the message that would you like to send to all the students that are watching us right now in terms of the skills that they should develop, how to think about their future, how to proceed in the future? What would be the advice after?
Okay. Well,
Words of wisdom here.
yeah, maybe I'm too young for that, but I don't know. Different things, I guess. Keep an open mind first. I think, for better or for worse, it's unlikely that you're going to spend all your life in the same company or the same organization when you start working. So I think it's good to keep. I didn't think I was going to do that when I graduated. I was looking at other stuff, and this opportunity came up, and the timing was good, and I took it, and I think and I really liked it. So it's keep an open mind, especially if you do graduate studies. Sometimes you're like, yeah, I want to do research, or I want to work I want to be a professor at MIT, and it might be good, and this is what you might want to achieve, and this might be the path for you, but there might be a lot of other options, and other than pure research and things like that. So what I didn't like I liked research, but what I found not as enjoyable was somewhat slow pace, and things don't go very fast and things like that, which you don't have here. Things go quicker. Think a bit outside of the box. A lot of what I do is not directly necessarily pure, materials or corrosion and things like that, but so there's that, like, grab the opportunities that if you think you're going to like it, well, you can try it out. So I tried different things, and there were things I liked, things I didn't like, and same thing with the co-op work terms. If you're doing co-op work terms, try different things. So I did an industrial one. I did 3 kind of research with different types of, and that was a good opportunity. I saw how it works in a plant. I saw different things. I said, well, this is what I like, what I don't like, and also being able to communicate as clearly as possible from like writing good report or good papers, good articles, but also being able to present and do good PowerPoint presentations and things like that. And I think at McGill we're pretty good at that. Like you present a lot, and so this is good, but this is really a really useful skill. And also, how could I say that, like, soft skills are very important. So, and unless you're working in your lab and you're in the dark and something like that, like interacting with people is very important. And if I've worked with researchers in the past that were extremely bright but had a lot of trouble working with other people, and in the end I think they only achieved a fraction of what they could have done because they were in their corner, not talking to anyone or being disrespectful, or so and in the end, unfortunately, you got to work with others, so and I think soft skills are also very important, and I think in a lot of instances they're more important than hard skills. The hard skills you can learn, and you often now I start working on a project. I don't know that much. I'm not like it's like the biggest expert, but I'll learn as I go. If I'm not able to communicate my ideas, or I get in a fight or with my colleagues and things like that, that's the end of it.
So, closing this interview, what would you say is the challenges of the future for a forensic engineer?
Well, that's a good question. I think the issue is that things become more and more complex. Yeah, that's it. Everything is becoming more complex. Like let's say we talk about cars. In the past, cars you like basic mechanic could repair a car. Now there's more electronics or more things like that. So it's the same issue with what we're dealing with. Industrial processes become more complex. There's more instrumentation. There's more. So everything is becoming more complicated, involving interdisciplinary, basically skills and things like that. And I think this is the challenge we're facing is how can we work in a team to solve more complex problems and things like that. So for example, in the past, if you were working in a plant and there was a leak from a petroleum product, well, nobody cared. It leaked in the ground and nobody cared. Now it's a big issue. And so minor problem that in the past you could just ignore and be like, whatever. Now they're major issues. So I think this is the challenge is working in teams and working with systems. Codes become more and more complex. I have a colleague who specialized in pressure vessels, and he said when the first pressure vessel code came in, it was basically 10, 20 pages. It was stapled together and the cost was 25 cents. Now, the ESME code, the entire thing is thousands of pages, and they're obviously very expensive, but nobody is an expert in the entire thing. So you know very well some sections, but nobody is an expert in it. So I think that's the main challenge. I think is that everything, I guess, is becoming more complex and dealing with that.